Very good afternoon to everyone. I welcome back to the second session of first day in this FDP program. Here we are having our next speaker, Professor L Krishnanand sir. He is a professor in the Department of Mechanical Engineering at NIT Warangal and he is coordinator for this workshop also. Professor did BTech in Mechanical Engineering from VRSE Vijayawada in 1983 and MTech in Industrial Engineering from NIT Calicut in 1986. And later he joined as a faculty member at NIT Warangal in 1987. Subsequently, he did PhD from NIT Warangal in the year of 1999 in the area of automatic feature recognition from CAD. His research areas are additive manufacturing, supply chain management, and project management. His paper on supply chain management was awarded Best Paper for Outstanding Conceptual Theoretical Framework in International Conference on E-Business and Supply Chain Competitiveness held in IIT Kharagpur in 2016. He taught project management at IIT Bangkok, Thailand as a visiting faculty in August 2003. And he's published more than 100 research articles and more than 10 book chapters. And also is a professor in the Department of Mechanical Engineering. Today is going to handle the session on this medical scanning technology for 3D printing and all. I heartily welcome to Professor Krishnan sir. Over to you, sir.
Okay. Thank you, Dr. Manjaya, for the introduction. So, anyway, handling the afternoon session is a bit tough job because some of you might be a bit tired attending the inaugural function and everything. And after the lunch, sometimes you tend to doze off. So I try to make it as alive as I can to keep you interesting in my lecture. So just see, like, if see for medically see this 1 week workshop is mainly meant for medical applications. So naturally, the first input data that you need for additive manufacturing, that you normally source it from DICOM, digital image communication in medicine, DICOM. That format you will be using for so that you can later use mimics to convert it into STL file, and then from STL file to you transfer it to machine which will do slicing. Actually, the funny thing about this particular aspect is initially you start with the slicing only. Then you, from that slices, you try to reconstruct a 3D model which is in the form of DICOM format, and from that you reconstruct using mimics to give it a complete 3D format. So we are moving from slice to slice. So that is the paradox. So initially we get the human anatomy, you get the information about human anatomy in the form of slices, that is through CT scan. And again, ultimately what you are doing is slicing the you slice the STL file using various slicing algorithms, and then you try to construct the model layer by layer. Okay, so then why the medical information? Like, see, if you take X-ray is a 2D image of a body, but X-ray as such doesn't help us in reconstructing a 3D object. So for that, what people have done is they have gone for a slicing strategy, so that each slice again it is combined and made a slicing image. From each slice again you reconstruct a 3D object. So it is, there is a lot of process involved, and all this process involves a lot of computation, use of beautiful algorithms, right? So anyway, we will go through that entire steps, how this evolution has happened and how people have struggled to solve certain problems which we don't normally expected. You are not expected to even to imagine such problems can exist in such situations. So let me start my formal lecture by sharing my PPT. Actually, friends, actually to save the bandwidth, because I'm operating through a hotspot, I don't know how it will be. So at the outset, is my voice clear to you?
Yes, sir, it is fine, sir.
The slides are
Yeah, it's
also
visible,
fine.
sir.
Okay. So now let me just uh, what do you call? I will what do you call? Wait. So anyway, yeah. So this is. Let me start with the uh, my what do you call? Uh, so normally most of the medical images that you require for additive manufacturing, like for example, somebody had uh, a medical problem like AVN. AVN means avascular necrosis. In fact, mm, I'm also a patient of avascular necrosis. AVN, it is called as. Say this medical condition, what happens is it will slowly deteriorate your hips, right? So sometimes after some time, even though there are certain surgical interventions, after some time you may have to go for total hip replacement. Fortunately, I have not reached that stage, but when you go for total hip replacement, see now with this computer CT scans, computed tomography, you can customize a hip replacement with exact suiting to your body dimensions or requirement, because each man's hip size and the socket and all those things they may change depending on like how much height, how much weight bearing capacity, other personal what do you call dimensions come into play, and you can't use a standard hip to replace the original hip. So in that way, so first of all, what you do, you have to reconstruct. You have to using a CT scan. You have to get the 3D profile of the 3D form of the hip bone.
Hello, sir.
Am I audible?
Yes, sir. Yes, sir. Fine, sir. Now.
Okay, okay. So, just 1 minute. I will switch off my. Is my screen is visible?
No, sir. No, sir. Share the screen, sir. Then you can switch off the video.
This screen is visible?
No, sir.
This one. Oh, wait. Sorry.
Sir, can you able to share the screen, sir? Now.
Yes, I
Yes.
will do.
Yes.
Is it visible
Yes,
now?
sir. Yes, sir. Now, fine, sir. Yes, sir. Now you can switch off the video, sir. Yes, sir. Fine, sir. Go ahead.
So now, friends, sorry for the interruption. As I said, now I'm operating through a hotspot because the place I'm present doesn't have. So this, so he's like Johann wrote a radon in 1917 itself. He proved that it is possible to reconstruct or build up an image of 2D or 3D object from a large number of its projections from different directions. So it led to applications in many fields ranging from electron microscope to astronomy. All right, because see, to construct, for example, to reconstruct the entire universe, unfortunately, a telescope or a radio telescope can see only one slice. It can take one slice of the astronomy. Similarly, here, this radon, Johanna radon, he, uh, he was the one who visualized that we can construct a 2D image or a 3D image from large number of projections. So, and computed tomography, tomos means section. So when you take sections, so you're able to reconstruct a 2D. See, for example, it is like whereas in conventional engineering drawing, you have top view, side view, and front view, right? Using that, you can reconstruct like a 3D image. But to reconstruct an irregular object, you need a lot of particularly human anatomy. It requires a lot of projections from different directions. So, so let us see like who are the people who did a lot of work for us. So he is the man. You can see like here uh, in 1963-64, like he developed solutions, mathematical problem to mathematical problem in CET at physics department in Tufts University. So he formed the basis for future work by Godfrey Hounsfield. So in fact, like he was he was given Nobel Prize in 1979 to this Alan MacLeod. So these two people, like he is the Godfrey Hounsfield. So he did that. Uh, Coming to this man, he is again a very innovator in the sense he developed this technology by working with electric and music industries, EMI. And for this, what he did is, as it is written here, it is partly funded by the Beatles, musical group. See, he has approached various research agencies in UK. Everyone have turned him down, saying that this will not work. And so when he went to Beatles, they partially funded him because they at that time their songs got so popular, they got so much money, they don't know what to do with their money. They thought like here is a man who said like he will do a lot of things. So they thought like we will fund this man. So like the EMI people finally funded this research. And can you recognize this figure? Can anyone guess what is this apparatus? Can you guess what is this? What it looks like? Yeah. So
Camera.
this is see, this is actually he has used a conventional lathe. He converted into a, a CT scan. And for this, see, to test his what you call uh, idea, what he did is he has taken an object and he took around 28,800 projections around that. He has mounted that his X-ray on a what you call on a tool post. He moved the tool post around the job to take the image, sense the radiation on the other side. So here 28,800 means it is not a simple one, right? So and finally he succeeded in getting the whatever. From that he made lot of improvements and finally uh, see you can say like he has also named his first machine as EMI, electric music and electric and music industries. So in a way, like so that's why he has called his model as EMI Mark 1 in 1971. It is the first clinical prototype brain CT scanner at Atkinson's Montreal Hospital in UK. So it is the first it did the first human scan in 1972. Even though it was introduced in 1971, they were till then they were trying on various other animals kind of stuff, because to ensure that the uh, the the people will not end up receiving a lot of radiation, unnecessary radiation. All the experiments were being done using some animals other than humans. So this is how a CT scan will look like, and most of you are familiar with that. So here you have a gantry with a rotating tube and detectors and cooling apparatus, because it generates a lot of heat. X-rays. Ultimately, they are using X-rays, so naturally they generate a lot of heat. So, and this is a motorized table which goes into that donut-shaped ring, and then and there is a computer with with console for image reconstruction and viewing. So this is the normally the arrangement what we see in any CT scanner. So almost MRI also looks in the same manner, but here, whereas MRI is totally based on a different strategy, and we will not be using MRI for our additive manufacturing, because MRI concentrated more on muscle, whereas CT concentrates more on bones. So because mostly the uh, replacements that we see is bone replacements mainly. We use additive manufacturing for bone replacement. Huh? So that's why. So here you can see here there are the blown up view of the same CT scanner is looks like something like this, right? So most of the routinely performed scans acquire multiple 2D images in the form of slices or transverse sections, axis sections oriented perpendicular to the axis of the patient. So that is how you do CT scanning, right? So, so what is the working principle here? So the concept is like, hello, madam, what you want? Madam, your voice is not so clear, madam. Hello, hello.
Please carry on, sir. No problem.
Huh?
Yeah, carry on, sir.
Korean. Okay. So, um, so the entire scheme of things revolves around the concept of attenuation. So, attenuation is the reduction of the intensity of an X-ray beam as it transverse traverses traverses the matter. Okay. So here you can see that this is the, let us say this is the muscle, right? And the X-rays contain photon energy. They penetrate this, and so you see there is attenuation of the signal to the extent of, like, that's why there is a degradation in the signal. So this is what happens. So, like, some part of the attenuation is due to the absorption of the photons by the muscle, and some thing is through scatter, like it gets diffused here and there, and then so, like, this there is a what you call, for each type of muscle there is a density atomic number, it's called Z. So which it depends on the kind of composition of the muscle. So through this Z number also, like we can estimate this Z number also. It is a property of steel which can be summarized as the linear uh, attenuation coefficient for a particular X-ray beam composition. All right. So this is the concept of attenuation, and using this concept of attenuation, we try to reconstruct the slice of a cross section of in this case human being. All right. So so this how this attenuation it follows a like this linear what you call this linear attenuation coefficient is which is indicated by mu, right? So it is like that is nothing but Ix, that is intensity of the incident ray X-ray beam. This is then intensity of the exiting the what you call the material and thickness of the material. So the the X-ray beam exiting the material is a function of the incident ray as well as thickness and the linear attention coefficient of the material. And this linear attention coefficient of the material is a function of the, it depends on the characteristics of the material through which it is. So, and unfortunately or fortunately, human muscle consists of various kinds of, it is not a what you call a homogeneous material. All right. So it the X-ray should pass through muscle, blood, you know, bone, and this attenuation happens in different ways depending on the attenuation coefficient of the material. So we need to, so when we are taking slices, we should also be guessing what is the linear attenuation coefficient of each of those materials. Why we have to estimate is, let us see in the subsequent slides. So here, this is the, you like if you take here, this is the, let us say this is the material through which the beam is going out. It is coming here and it is going out. So if you break this muzzle into say a kind of pixel kind of stuff. So here there may be a blood, this may be something else, this may be a muscle, this may be a bone. So depending on the characteristics of the material, depending on the attenuation coefficient, the whole beam comes out with the various levels of attenuation, depending on how it is passing through the body, whether it is passing through a combination of blood and muscle and bone, or simply skin, or simply blood. So here you can see the intensity is coming down, but attenuation is going up. Attenuation means degradation of the beam. So naturally, when the intensity is going down, means attenuation will automatically increase. That means there is a degradation in the. So this fact is used. So here, what we are doing is like this is the inlet or in which the beam is passing out. Then you can see that here we have some unknown variables like mu1 d1, mu2 d2, like that mu1 dn, right? So out of that, like, but inlet input intensity and output intensity. So and we have to guess how much distance of in this distance, how much, what is the local attenuation coefficient. So how to guess this? Because unless you know all these attenuation coefficients passing through each of the layers of the human muscle and bone, you cannot construct the attenuation profile. So because based on that attenuation profile, you can reconstruct a 2D image. So let us see like how this man has solved. So such equation can be generated for all acquired projections. So this is how, like, you can see, this is how, like uh, X-rays are coming from this side, and this is a you can say CCD uh, detector area made of CCD, charged coupled devices. So on that the X-rays, after getting it, say like this is the human skull, right? See, you are trying to take a slice of the human skull, so you are passing through a series of X-rays, and it is penetrating through the skull, and it is getting like it is getting dictated by an array of detectors. So depending on how that particular array has passed through, either through blood or through bone or brain tissue, it correspondingly get attenuated, and you get this. Similarly from this side. So like that, you can say in a sophisticated maybe you take this maybe around 120 slices, not 120 slices, like depending on 180 or 360 degrees, you take snaps of it, and then what you do is individual attention profiles of multiple projections, you get it, and you get the final image. Image reconstruction algorithm, you use image reconstruction algorithm, solve for attenuation coefficients of each pixel using equation generated for each projection and its respective attenuation profile. So that is the how, like, you generate like the final image. So how these, using these reconstruction algorithms, so you get a attenuation profile like this, right? See, all attenuation profiles. This is called as sinograph. So this we got it on a for a single slice. So from this single slice, you, you have to construct the 2D image of the slice. So for this, what they do is they use lot of what you call image reconstruction algorithms, right? So here, so this is a like here we can see like strong attenuation, how it is depicted by white area, because like more attenuation happens if X-ray beam is passing through a bone, but whereas weak attenuation may happen if the X-ray is passing through, say, a liquid like blood. So the attenuation, the amount of attenuation depends on how the X-ray beam has passed through a particular medium, either it is bone or a tissue or a liquid like blood. So here, that is, so using these sinograms, series of sinograms, so like for example, this is the series of sinograms, people got it in one round, right? What they do is they consolidate this one round of it and get this. See, actually, like B is one way, then uh, 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 consolidated few things you get see Hello?
Hello, sir.
Hello, participants?
Yes, sir.
Oh, there is a small disruption.
Okay, sir. Okay, sir.
Yeah. My screen is visible?
No, sir. No, sir.
No, sir.
No, sir.
This side is loading. Yeah, it's visible.
Yes, sir.
Yes, yes, yes.
So here,
Processing.
what you see here is that we get a blurred image like here, right? See, actually, we should get this kind of image, but we are getting using this simple crude reconstruction algorithms, we get this kind of image. But this we don't, from when we get this kind of image, it is of no use. So what we do is we use some kind of filtering techniques to increase the sharpness of the image. So what we do here is that we play with amplitude, frequency, orientation. Anyway, let us not go into the details of the spatial frequency. Finally, the idea here is, like for example, like if you see here, using this so here what we do is hello.
Yes, yes, sir. Yes, sir. It's a hearing.
Okay. Because in between there is a break. I'm just wondering whether people are listening or not. So here using this, like using low pass filter, what you can do? Uh, yes. So using this kind of, so this is the principle with which they try to, what do you call, clean the image so that noise part of the image is eliminated using these high pass filters and low pass filters depending on the image situation. They know, like for this particular image a low pass filter has to be used, whereas the other one a high pass filter is needed. So if you need high good rough edges, maybe low pass filter is good. If it is you need rough edges, maybe high pass filter is needed. Like that. So people like that is how like people have developed things. So here using a ramp filter, right? So what they do is they try to change the profile, like they increase the, see for example here there is a blurriness of the here, but here what we do is like when we use this, so we increase a bit of contrastness and the clear lines are there, right? So using this filtering strategy, we can increase the sharpness of the image. So using low pass filter or a high pass filter, depending on the situation, they try to increase the clarity on the image. So here, say for example, like back propagation filter, back propagation. See, for example, if you are using like you project from here, you get a blurred image here, and if you back propagate, you get a blurred image. But whereas you use the same image, you use a ramp filter, it will increase the clarity, and then this you back propagate the, so you are able to see the two dots. One may be some bone and the other may be a muscle. You are able to distinguish. So how this is done, what do we mean by filtering mechanism is, like here you can see that, whereas here what you see is that, like you taking three views, one view, two view and three view, you are getting a, using three views you have constructed and you got a blurred image. But what you are doing is you are cutting off the rough, some unnecessary things you eliminate it, so that you are able to get a more clarified image of it. So this is how like people started improving the clarity of the image by using this filtered back projection, projection. Like simple back projection is this one, whereas filtered back projection means this one. So using filtered back projection, you are able to get more clarity in the image. So you collect all those clarified images and then try to get it. So here you can see contrast between. So this is the with just simple back projection, whereas this is what I call filtered back projection. So we have filtered out. So that's why you can see here very sharp lines at the borders, right? So in that way we can get all the beautiful details. See, this is the original profile of the cross section. This is, and whereas if you are using simple back projection, you get only this. This you got it from using from various projection angles. Okay, whereas here, whereas in the second case, since you have used various filters and then removed all that noise in each of those projections, so you got a very sharp image here. So that is the how you generate profile, that you generate each slice information like this. So here what we do, see, this is how like we generate the slicing information. So here you can see image sharpness and noise, right? So a comparison. So here also what we do is like whereas if you take this one, like if you take this one, normally we mechanical engineer, we think that this is this image has a lot of noise, but actually this image has a lot of information, whereas this has more what do you call this has actually more noise rather than this. But for our situation, we need this bone skull information, because we are not interested in muscle information. So you can compromise on, by compromising on muscle information, you can get more clarity on the bone information of the CT scan. Right? So that is how we have to choose the filters. What kind of filters? But anyway, fortunately, don't worry. See, all these steps are being automatically done. Like using now, people are using a lot of AI tools like ML, machine learning, and deep learning. In fact, like most 90% of the work will be done by CT scanning machines. So don't worry, this is only to understand the underlying technology. See, whatever I am saying here, this is only to know what is happening in the background. Okay, so here what we do is uh, this. So you have to make a trade-off between sharpness and noise. So depending on your, if you are interested in muscle, have sharpness. If you are interested in bone, maybe noise is also okay. Okay, so depending on the ultimate use with which you are going to use this slices and reconstruct that, depending on that you do it. So then there is another strategy called iterative reconstruction. Here also we do like you measure the projections and then again see whether how the image has come. If you are not liking the kind of attenuation here, what you do is you try to make a synthesized projection and then do it. So this is an iterative reconstruction. So here we either back projection like filtering strategy is okay, or this one is also okay, but depending on the situation one can use it. See, I'm not going to explain this algorithm because we have to cover still more so here this is how like you do like if you first image estimates will be you get it, then if you the corrected images, if the corrected image is not good, then you again go for simulated projections or corrected projections and compare it, and then and you try to take you try to do it iteratively because there is nothing but it is all mathematics. So you can change the filters and other things as you do it, right? So this is when you go for filtered back projection or iterative projection means here like filtered back projection is prone to noise and artifacts in low dose conditions. So here what we mean by artifacts means it is see sometimes artifacts means it is unnecessary things that can exist in the body, or it can be because of error in our computation also, or sometimes like for example somebody has some implant already, some like for example some uh, titanium implant for thigh bone. So that is an artifact which can spoil the scanning because it is a metal. So when X-ray hits on it, there is a lot of scattering happens. So that scattering will spoil the that issue. So here what you have to do is you have to take the necessary precautions for that. See, you can't ask the patient to, you can't ask a patient like we will do perform the surgery and remove that one implant because that is fixed. So instead of that, you can do some kind of you can use some kind of calibration approaches to overcome such artifacts. So prone to noise and in low dose conditions, poor low contrast stability in low dose conditions. So because you're using a lot of filters now in filtered back projection. So hello, somebody wants hello. Anyway, so computationally robust and less time intensive allows rapid processing because say there is no human intervention. Whereas here, noise and artifacts are easily modeled and excluded compared to. So this is what I said. Like if you have artifacts, you can calibrate because you are doing in any way, iterative way. Maintain image quality in loader. So you can even in those conditions, image quality is maintained and computationally intensive and has long processing time, especially in older systems because see you are doing it iterative way, right? So particularly it may take because if you are using CT scans very comfortably now, we have to thank one law. it is called as Moore's law of computing. I don't know whether some of you are aware of. I am not able to write it here. So anyway, Moore's law of computing, due to Moore's law of computing, we are able to do a lot of uh, do all these computationally things, intensive things. So here we have what is so-called Ct number or Hounsfield number. See, this man, Hounsfield only invented that lathe-based first EMI machine, EMI Mark 1. So in honor of him, we said it is a kind of parameter we use called Ct number. So this is a kind of commonly chosen magnification factor K for human imaging is this Ct numbers changes with the medium in which the X-ray passes, right? So they have just like IC is taken as a standard to develop 0 to 100 kind of, see, boiling of water is given 100 and then what do you call ice is 0. So similarly here also we have given for water this HT number as CT number as 0. Water baseline is 0, right? And particle bone is 1000, and whereas air is -100. So the CT number obtained for each pixel is represented on a grayscale, generating a grayscale. So on a grayscale pixel image, which is akin to a bitmap computer. So such images are generated for each of the actual slices perpendicular to anyway. As slice thickness and interslice gap are known, interpolation algorithm generate cuboids, voxels, by interpolating pixels with adjacent slices, thus generating a 3D voxel representation of the entire volume image. So that is how each slice information is generated. Here you can see this voxel. So when thickness is added, this slice width is added, a pixel gets converted into a 3D element. We call it as voxel. So Hounsfield numbers like the 3095 is the maximum one. Bone comes at 1000. Water at, so air is given a Hounsfield number of -1000. So based on this, you can identify whether the given image is a bone or a water or soft tissue, whatever it is. So Ct number for each of those materials, tissue types, it changes. So this is how you calibrate an image. So here, like for example, like if you take so if you take this example, so here what we see, like you have wide range of Ct numbers that may many levels of gray. So say for example, if you take our computer screen, if it is a 8-bit plane, each pixel can afford to have around 256 shades of gray. So normally in each pixel in a computer color monitor, it will have 24-bit, because 8-bit for each what you call basic color like RGB. So if 24 bits are given, then almost 16,000 16,000 million colors are possible. You can depict them in number. Similarly here, but we don't need so much shades. Here, human eye can perceive no more than 900 shades. So it is no use in having so many big planes for each pixel. So here, what we are doing is like so here in the to increase the smooth construction and sharp reconstruction. So you have what is so called brain algorithm and bone algorithm, because each need a different strategy. As I was telling before, now. So whereas in brain, the sharpness is high, whereas here there is more in bone situation. The noise is more because we are not able to distinguish between different parts of the brain. Like whereas here we can see clearly the shade difference, but here it is more granular. But at the same time, our interest is the boundaries. So when boundaries are important for us, so naturally we go for a bit sharp means more noise. So by changing the window width and window level, we can choose the appropriate images to, what you call configure as per our requirement. So here you can say sharpness is more important when inherent tissue contract is more, right? Whereas noise reduction is more important when inherent tissue contrast is less. So the solution is selection of appropriate kernels for filtering. So this is how like, but anyway, as I told you before, all this information is only for you to understand the underlying technology. But most of these steps are now automatically executed in a CT scan. So anyway, let us come to the how this evolution of the Ct Gantry has come. So instantly, the first generation CT scan is pencil beam with translate rotate trajectory. So here what is happening is I will just quickly go through this because anyway, so what we do is in a single round, what we do is it rotate, then translate, and then rotate. So that is the strategy with which, so with this they at 180 views they used to collect, and 160 rays per measurements per view. So there is this linear detector, right? Single detector used to be there. So that is how, like, say for example, this 28,800. So 5 mm per slice. This is how like they got the. In fact, like when David or Hounsfield, when he first generated his image, he has used around 28,800 measurements. He has not used X-ray. Instead, he has used some what do you call gamma ray, some crystal like a radioactive element to generate the rays, and at the other side he has used some CCD crude CCD device, so that he can measure the attenuation of each ray. So that is how like he did it. So probably this is the kind of strategy our Hounsfield might have used to generate the first images of each slice. And then we have a second generation where it is a fan beam and translate rotate kind of strategy. So the X-ray is you can see here. So this is translation, then rotation, translation, rotation. That is the strategy here. So rotate, translate, rotate kind of So this has simplified. The number of views is 6, and made possible by a fan beam of 3 to 10 degrees, and then along with multiple detectors, up to 30 detectors simultaneously recording the incident. So here, there it was only single beam, but here it is an array of 30 detectors were there. And then anyways, third generation, you have what you call with it is only just rotate trajectory. Fan beam widened to encompass the entire object, eliminates translatory motion. So you can see this fan beam is covering the entire skull. So this is the, let us say this is the skull or whatever it is able to cover the entire. So here he has increased the number of detectors here, right? Detector array. So using stable detectors, monitoring chambers, so they ended up getting this. Then as little as 1% error in X-ray output or detector calibrate can lead to. So see, as I said now, so it can lead to artifacts means, see, this is the nuisance, like if those rays which are just tangential to some object or there, it can lead to some kind of artifacts. That means artifacts means those um, images which which it doesn't make any sense. So so for that, what you have to do is uniformity of response, precision of detector electronics, and algorithm corrections needed to prevent artifacts. So you have to do some kind of, even though in one beam you are able to cover the entire section, but still the other nuisance is like you may end up having some artifacts. For that, you have to do necessary correction algorithms you have to use. And then you have fourth generation fan beam with rotate trajectory, stationary, circular detector array, right? So now the detector array is constant. The fan beam is rotating. So previously, both the detector array and as well as the fan, the beam used to rotate. Now with the stationary circular detector array, have all the advantage of third generation scanner in terms of speed and less prone to artifact due to detector calibration errors. So less popular due to high production and maintenance costs. And then fifth generation CT. So there are no moving parts. So electron beam is electromagnetic deflected and focused on an extended junction anode target arranged semicircularly around the patient. So here now even beam is not meant to move. So using electron beam and a deflector, so in thereby what is happening is it can sustain high tube currents for a long time as only part of the anode is exposed at any point of time. So the anode is around, right, to an extended junction anode target. So what is happening is generates up to 8 high resolution slices in 50 microseconds. Can produce cine images of moving organs like the heart. So this, by fifth generation, you are able to even previously only inanimate things you can do in CT scan, but now even animated organs like heart also can be, because you are taking resolution slices, 8 resolution slices in 50, so you get a movie camera kind of depiction of the organs, particularly heart. So, but highly expensive, hence less popular. And then sixth generation is like what is called helical spiral Ct. So simultaneously source rotation, table translation, and data acquisition. So so source rotation is there, then table rotation So simultaneously happening, so you need not stop for every round. So one continuous volume of entire region allows easier 3D. So larger Z-axis coverage in short span of time useful for moving organs, patients, ECG gating, single breath-hold equation, and larger angiographic equations with single bolus of contrast agent. So that means, like for example, you can see nowadays people are doing interventional neuroradiology or interventional cardio. Like for them, this sixth generation CT, they use sixth generation CT because they can get a larger angiographic equation with a single bolus of contrast agent. So you can get even clearly the blood vessels and how the blood is flowing, all that. So dynamically you are able to see what is happening in the patient's body, right? So it is helical, and then we have three technological improvements which made it possible. That is slip ring electrical energy transfer, and then efficient interpolation algorithms for generating volumetric data from multiple helical slices, X-ray tubes with high heat capacity which can sustain long continuous exposure at a time. So because deflected extended tungsten element is there now, so it is done. It is there in the entire tube, so circularly. So sustained high heat capacity can be sustained, and say, using slip ring electrical energy transfer, you are able to do that spiraling thing. And then when we coming to seventh generation, cone beam and multiple parallel rows of detectors. So four detector array in, and then detector like for example, this is you are able to have four detector arrays at a time, and in each detector array, like you have so many individual detectors. So you are no more taking simply one row of detectors. So you are taking a rectangular uh, thing. So that is actually creating a kind of, you are getting directly a slice, right? Multiple 4 to 64 slices simultaneously. So that is the beauty of it. So the advantage is reducing scan time, increasing Z resolution compared to sixth generation, because Z resolution, like even a Z resolution, it is no more a single row. You have simon at a time 4 detector arrays are there, and in each detector array, like individual detectors are there. So it is a kind of less scatter rejection compared to single slice. So this is one, and here like you have. Detectors, how the ideal detector should have high efficiency, a low response time, then high dynamic range, and then a low afterglow. So this is another nuisance, low afterglow. Like you, particularly those who are using tube lights in their homes, even if you, after you have switched off the tube light, there is a small afterglow after some time. So gradually that afterglow will go off. So that nuisance is also there for in this kind of X-ray tubes. So you should have low afterglow and high resolution and high stability. So that is how like so now coming to performing a scan, common variables to keep track of is like focal what you call spot size. So here, what we do is how to choose the focal spot size. So it is uh, inversely related to detail, right? Increased detail requires decreased focal spot size. So here, how you are going to choose? See, this is the example of this is tooth of a human being, right? How you try to increase the sharpness here. So here, what you is up by increasing by adjusting the focal beam to here, choosing the appropriate angle. Like you can see, like there is a unsharpness to the extent of only this. Whereas if your effective spot beam is instead of like this, if you are keeping like this, then you can increase your sharpness. So here flying focal spots Siemens Tomatomo allow for slight change in focus, increase in data points, and the sampling increases. So in fact, these are all proprietary strategies used by Philips, Siemens, and GE. Like these are the three main players in CT scan. So these people, certain technologies they hide from our users. All right. So using focal support size, you can by increasing the overlap, you can increase detail require decrease focal support size. So it's not so it is MA dependent and automatically selected. So don't worry. Like the as I told you now, like most of the settings are now in the modern CT scanners. Like the machines are very intelligent now. They do a lot of adaptive what do you call, they can self learn and try to improve. You have to only tell like which tissue you are interested, whether you are interested in first of all in tissue or in bone details. If it is tissue, what kind of tissue is it? Muscle tissue or some other tissue or liver? So don't worry if some of these terminologies are not clear at present. So because so you can even say, for example, you can say like detector size and spacing. So like here in z-axis and in xy plane, inversely related to detail requires decrease size and space between detector elements, right? So this is obvious, no? Like decrease the size of the detector will automatically increase the sharpness. Detector size or spacing is not a selection made by technologies. It is dependent on the make and model of CT scanners. So water detection shift further increases the resolution. See, it is same as like some kind of what do you call in additive manufacturing also to improve the density of material in each slice. We do some kind of overlap now. So similar strategy we can use here to increase the resolution. So here you can see one image is without overlap. No 1.5 shift, and this is with 1/4 shift. So this 1/4 shift overlap will automatically increase the resolution of your image. So in fact, like these are some of the strategies people use while taking CT scan. How much overlap? So some things may be with us. Maybe sometimes, see, like myself and Y Ravi Kumar, we did some kind of error compensation strategies for imaging. So there with Manmadachari. So there we have come up with some kind of strategies to improve the resolution. All right. So using say the current and then field of view, FOV kind of parameters. All right. So similarly here, previously people used to do a lot of PhD work in this, but I think now it is matured subject and most of the things are being done by the intelligence of the machine itself. So instead of human intervention in increasing the sharpness of the image. So here, so so it refers to the sampling frequency, refers to the number of projection directly related to spatial resolution. Increase sampling, increase detail in a image naturally enough. So this is accomplished by increasing the sampling rate or the speed at which the detectors are read. So depends on the aftergo limitation of the detectors, and detector electronics usually not manually adjustable. So you can just only tell these increase or decrease that to certain within certain range, right? The sampling frequency, and then this field of view. So field of view again, this is explained in subsequent what you call slides. So pixel inversely related to detail, smaller is better, right? And then matrix directly related to detail, bigger is better, right? So matrix, see, whenever we purchase mobile cameras, mobile phones, we want say 16-bit, 16 megabyte pixel camera or 32 mega pixel camera. Like now, every cell phone is giving a fantastic. In fact, your mobile phone has uses lot of these reconstruction algorithms. I don't know whether you are aware of it. Like it can take care of your hand shakiness. So even though you may be pressing a photo in your using your camera when you are taking selfie, even if some people are a bit moving, it will compensate for that. So even though you are pressing once, it will take simultaneously 4 or 5 view of the same photo using some uh, algorithms, reconstruction algorithms. It will come with a very clear view of the picture. So though people are using
Sir, Krishnanand sir.
Sure, nothing is audible. Hello.
One second, sir. Hello. Dear participant, please. We'll back to you. Present here. Hello. Audible?
Hello? Why it is not connecting to audio? It is taking so much time. Hello? Who is taking the lecture now?
Audible, sir.
Hello?
Sir, you are audible, sir.
ఓకే ఓకే యా యా ఇది మంజీ గారు
Sir.
మీరు కనెక్షన్ పోయినప్పుడు మళ్ళీ మీరు నా సెల్కే కాల్ చేస్తున్నారు అదేమో మళ్ళీ బ్రేక్ అవుతుంది
Sir. అవును సార్.
సర్లే సర్లే ఇప్పుడు వినిపిస్తుంది కదా మీకు
వినిపిస్తుంది సార్, వినిపిస్తుంది సార్. నో ప్రాబ్లం.
ఓకే ఓకే నేను ఇంకా ఫ్యూ స్లైడ్స్ ఉన్నాయిలేండి జస్ట్
ఓకే సార్, ఓకే. గో హెడ్ సార్, గో హెడ్ సార్.
ఈజ్ ఇట్ విజిబుల్ హలో
ఇట్స్ లోడింగ్ సార్. లోడ్ అవుతుంది సార్.
మీకు కనిపిస్తుందా ఇమేజ్ షేర్
No, not yet, sir, not yet. Sir, are you sharing, sir?
హలో
Hello, sir.
అదే అదే ఇది షేరింగ్ కి కొంచెం బ్యాండ్ విడ్త్ ప్రాబ్లం వస్తున్నట్టు
Sir.
జస్ట్ వన్ హలో హలో
Hello, sir.
ఇది ఏదో హలో మంజయ్ గారు
Yes, sir.
ఇది నేను మిగతా తక్కువే
Sir, sir. You can orally you can explain, sir. No problem. Your bandwidth is very low, sir, I think.
హలో హలో హలో
ఎస్ సార్, ఎస్ సార్.
ఈ కొంచెం ఏదో బ్యాండ్ విడ్త్
రవికుమార్ సార్.
హలో
ఎస్ సార్, సార్ ఏదో బ్యాండ్ విడ్త్ లో ఉన్నట్టుంది సార్. అక్కడ ఏదో నెట్వర్క్ రావట్లేదేమో సార్.
ఓకే. హలో హలో
సార్ చెప్పండి సార్.
ఇది ఏదో బ్యాండ్ విడ్త్ ఇష్యూస్ ఉన్నట్టున్నాయి.
సార్ సార్ జాయిన్ అయ్యి వెంటనే వెళ్ళిపోతున్నారు సార్. అది రవి సార్ మోస్ట్లీ అదే జాయిన్ అయ్యి ఇమీడియట్ గా పోతున్నారు సార్. అది డిస్కనెక్ట్ అవుతుంది.
ఓకే.
ఏం చేద్దాం సార్?
ఇంకెంత ఉంది ప్రెజెంటేషన్?
3 slides ఉన్నాయండి సార్.
కన్క్లూడ్ చేసేయమనండి, లేకపోతే వాయిస్ తోనే పని. అది కూడా రావట్లేదా?
జాయిన్ అవుతున్నారు, పోతున్నారు సార్.
ట్రై చేయమనండి, లేకపోతే కన్క్లూడ్ చేసేసేయండి.
సార్ ఓకే సార్.
సార్ లాస్ట్ అటెంప్ట్ ట్రై చేయమనండి ఓరల్ గా చెప్పడానికి. అదర్వైజ్ యూ కెన్ కన్క్లూడ్.
Joining in 5 minutes, sir. Participant be in the link and sir is going to join in 5 minutes in another PC.
Hello? Hello, participants?
Yes, sir. Yes, sir.
Just one minute. Oh, you have pen drive? Right. Small pen drive. In Bangalore. So actually, is it visible?
Yes, sir. Visible, sir.
So there are just a few slides left over. Sorry for the interruption. So we discussed this sampling frequency, then like the sampling frequency increases the sharpness. So here this is accomplished by the sampling rate or the speed at which is read, but you have the problem of afterglow limitations and the of the detectors and detector electronics. So these are not usually not manually adjustable. So it comes with the hardware and you can't do anything with respect to this. So afterglow. And here, so you have field of view. Anyway, we have discussed this also. Like it is a combination of like the pixel size. Normally pixel is the smaller is better, the matrix is bigger is better. So anyway, technologies doesn't have control on the pixel size or the matrix directly. So so field of view anyway it is technologist can control this because see the smaller is better. All right. So technologies can also adjust the kernel for filtering, which in turn inversely relates the spatial resolution and noise for given data set. So you can so these kernel and the FOV you can have the flexibility, right? So that is one. Then another important parameter is slice thickness. So inversely related to z-axis spatial resolution. So increased sliceness scan or viewing decreases the detail in an image due to partial volume averaging. So thinner the slice, poorer the signal to noise ratio for a given dose. So averaging 1 mm slices into one thick 4 mm will increase the signal by 4 times, but noise will increase by root of 4, that is 2 times. So here you have to use some kind of aggregation methodologies to do some kind of manipulation. So in this image, you can see the clarity on the, and then we have the another thing that so it is this pitch is inversely related to z-axis spatial resolution. So increased pitch decreases detail in an image due to partial volume averaging. So lower the pitch, higher the signal to noise ratio. So so lower the pitch, higher the radiation dose. So when you are, that means you are putting patient into a bit of risk if with the higher radiation. So you should see the patient interest also. So this is a multi-objective function. Multi-objective function of radiation dosage and signal to noise ratio. Then all these things you should consider when you are taking a slice of sliced image of a patient. So this is, so another important thing is this is indirectly related to noise, and this is milliamps milliamps second. That is, this is directly related to contrast resolution. So just 1 minute. So the full form of this MAS means milliampere second. So here this is under the control of the technologies. So if you are increasing the milliampere seconds, and that means for how many seconds you are exposing the patient to such a high current. See, because again, the more the current means more the radiation. So you have to, this is in the under the control of the technologies. So again, you have to decide whether higher radiation is important to get a, see, when you increase the higher radiation, you get a more good picture. But at the same time, you are also putting the patient at risk. So you have to make again a trade-off there. Whereas KVP, which is kilovolt peak. So this is again anyway, this is also higher the better quality, but it also exposes more radiation, and normally this is not under your control. So this is another aspect you have to so you have to take care of. So and then so here you automated tube current modulation. This is normally it is used in the case of say like automate partial volume averaging. So here like another important thing that one should be aware of is this beam hardening issue. So here, if you, for example, if you use a cylinder and if you expose to radiation, the attenuation will be not uniform. So the attenuation will be at the edges is very less and it is more in the middle. So here, again, this beam hardening also is partly under your control. So this similarly, how much current modulation. So that is also you try to so main parameter is this. So MAS you can correct it, you can control and get a clarified image. Then KVP is not in under your this KVP is also under the control of the technologists, but due to complex relations with contrast resolution, it should not be first step to decreasing noise in an examination. So this is anyway, now it is taken out of the user. So the machine itself will decide how much kilovolt peak, how much voltage you should apply for increasing the signal strength. So this is automatic tube current modulation, and then we have artifacts correction. So artifacts, I told you, it is a kind of unnecessary, unrequired images that you may end up getting because of errors in computation or because of the some foreign objects present in a patient. So here again, for beam hardening, for compensate for that, beam shaping filters, calibration correction, iterative reconstruction, pre-hardening. Like pre-hardening strategy means you increase the radiation to compensate for the this loss of information. So that pre-hardening, that means you increase the you like error compensation kind of strategies, right? So this, and then we have this field of view issue is there, and partial volume, using partial volume averaging, you should also able to again, this is again another concept. I think it will take time to explain, but the main purpose is thin acquisition section widths are possible, and then there is an issue of photon starvation. Photon starvation means like you get completely a blackout kind of situations can happen. That means you don't, in spite of your adjustment of mass and MEAS, the multi-ampere second kind of kilovolt peak, even after adjustment of that, sometimes you lose certain information within the body parts. So that is called as photon starvation. So this also you should be careful, because sometimes you may not be interested, but if there is a crucial bone is there inside of it, and it is of matter of interest for you in making the in making it through additive manufacturing means, then you may not get a complete model of the entity that you are trying to get at. So, so multi-dimensional adaptive filtration and then automated tube correction modulation. I think some of these strategies are being adopted, and in fact, like all these are now being done in the 7th generation CT scanners. So one need not worry about it. Like then I said about this metallic artifacts, like some woman may be wearing some earring, and then how it disturbs the whole. So for this again, you need to use some kind of calibration methods to isolate it. So here in the second figure, they have used some kind of calibrated strategies to improve the image. So, so correction C is screening for removable metallic objects before scanning, increasing KVP, matrix size, reduce slice thickness, iterative reconstruction software. So all these strategies are used to get it. So sometimes ring artifacts can come in. So again, some kind of find the culprit detector and recalibrate. So that is another correction things that you can use. And motion artifacts. Motion artifacts means like the patient sometimes will, particularly children, you can't keep them still when you are sending them into a CT scanner. So for that, you have to again work out some strategies. So like one is positioning and restraint. Like that means you put them, tied them with a belt, or sedation if necessary, and or shortening the scan time, reduce rotation time, increasing pitch, right? Then you do underscan or overscan modes. So software corrections for motion, reducing weight for end views of the scan. So such kind of strategies is also possible to increase the image. So then you have these step artifacts, right? Depending on the pitch and other issues like how much radiation, low, whether you are using low radiation or high radiation. So stair step. So for this, obtain thinner sections, right? For reduce the stair step artifacts. All right. So with this, so see, these are some of the issues I want to share with you. I think I have taken a lot of time to, and in between, sorry for the trouble, uh, because there is some kind of uh, what do you call breakage in the corrections. So, any doubts at this stage? Hello?
Thank you, sir. Thank you for giving a knowledge on this, the medical scanning technology for 3D printing, and what all, how the mechanism works in this, the CT scanning and all. You had given a lot of information and about the medical 3D process imaging and all, and how to converting the slicing, STL file conversion and all. Thank you very much, sir. And
Yeah.
participants, if you have any queries, please unmute yourself and ask the queries. Sir, one query is in the chat box. What is the full form of this KVP they are asking?
Huh?
KVP.
KVP, kilovolt peak.
Okay. Thank you, sir.
Kilovolt peak means like in the signal, like what is the maximum voltage you are getting in the scan during scanning.
Yeah.
So that
Any
you
other
have to
queries?
adjust.
Thank you. Any other queries from the participants?
I don't know how far they could assimilate.
It's difficult to understand some of the medical terms, sir. But
Yeah, and that too in one sitting.
yeah, yes, sir, yes, sir. Sir, one question, could you please share the PPT, sir? Yeah, we are sharing that video lectures and all once the FTP completes.
Yeah, yeah.
Is any other queries from the participant? Thank you, sir. Thank you once again. If there are no queries from the participants, we would like to end this session. And thank you for your patience and listening all the sessions from the morning. And sorry for this the internet issues happened in the afternoon. And thank you for your all cooperation, be in the online and carrying out all the sessions and all. And thank you very much. Please fill this the quiz form as it is posted in the chat box and as well as in the WhatsApp group. And we'll join in the tomorrow's as early as like 9:30 session. Thank you all once again. Thank you very much, sir.